So, welcome you all to the 8th problem solving session for this NPTEL course Principles of Communication System 1. We'll wait another 2-3 minutes for the audience to join and then we'll start. Okay, so let us begin. Just a brief recap what we have done in previous session. You can check out the recorded version of those. So what we started with is if you remember this ordinary amplitude modulation. I'm excluding the first two sessions because those are more about building the basics. Then we see its limitation and then we talk how double sideband suppressed carrier or DSBSC takes its place because in terms of efficiency, but of course it was not enough. There are better alternatives, so we come to single sideband modulation and vestigial sideband modulation, which is more practical than SSB. We talk about the different generating methods for how to get a single sideband modulation. If you remember the frequency discriminator or the and next in the last two sessions we have discussed extensively about the ADC, like analog to digital and digital to analog conversion, and how these are helpful in your signal processing aspect. Especially in last session what we discussed is core, something very fundamental to digital signal processing, which is Nyquist rate, which if you want to explain in a sentence, it's more like what is the rate at which you sample continuous signal so that there is no information loss. And the whole purpose of information loss is important because in signal processing you often move between analog to digital version, because of course your processing happens in the digital domain because it's much more efficient, whereas your practical transmission, like or the you can talk about any uh, signals in nature, they are analog in nature. So there is always this conversion continuously happening at the processing end, and then you process everything in the digital domain, then you convert it to analog, and then you transmit, and then at the receiver side the opposite happens. So in those conversions you have to make sure that there is not information loss at the ideal case, or practical case you should save the information as much as possible, and Nyquist rate just gives you a higher level idea how to do that. So today we are going to discuss something related to this analog to digital conversion, but something that is called quantization, which is very or almost equally important to Nyquist rate. Like why, I'll try to motivate why actually you need quantization and how it affects, and what are the different quantization methods that are basically used. I'm talking about the quantizers. Also we are going to see the later part of this session about different kind of receiver, like super heterodyne, stuff like that, but mostly this session is about understanding quantization and solving few model problems regarding that, so then you can go and solve the actual assignment problems. So let us move to our first question here. So the first question about the quantization, so it basically asks that what is quantization used for. Is it for to map a continuous time signal to a discrete time signal, or to from a continuous time a periodic signal to a power signal, or it is used to map a random continuous time signal to a deterministic discrete time signal, or its goal is to just sample a continuous time signal to a discrete set of values. So to understand that, let us briefly go back what we did last time. When we talk about analog to digital conversion, what we actually did is something of this sort. So if let's assume this is my original message signal, which is of course analog, continuous you can say. So we talk about taking few samples, right? Of course at a certain sampling rate, and if we call that sampling rate to be sampling interval, I would say TS. So it's like, let's say this is nTS, and this is at n minus 1th instant, and this is at n plus 1th instant. So this here we are getting m of n minus 1 TS, this one here m of nTS, and this one here is m of n plus 1 TS. So remember, these all are just some discrete values. Now the question is why the quantization is even coming to picture, right? I mean, it's all about having this sample. So what is actually quantization? So to understand that, let me write something. So let's talk about this particular one sample. This is actually a value, a discrete value. So you note that this is a scalar, right? This is a scalar that can take infinitely many values. And remember, when you talk about the digital signal processing, it's all about zeros and ones, right? So if let's say it takes a value something like 1.95, you cannot directly store it in its actual raw form. That is, there is no way you can store the actual 1.95. You cannot, right? It need to be converted some sequence of zeros and ones, because that's what all digital processing about it can you need to work with these binary numbers only, zeros and ones. So what happened, this can take infinitely many values, like, right? I mean, what I mean by that, let's say it can take value 1.95. Let's say it can, like, let's say MNTS takes a value between, let's say, 1 and 2. Okay, let's take a very simple example. It takes value between 1 and 2. Now how many values are there actually here? We can say there are infinitely many values, right? So similarly, this sample here can take infinitely many values, right? So let me point out something else. So when you talk about conversion of this number into a sequence of zeros and 1, so there is a relation first I'd like to talk about, that is the number of bits required to represent L values is log base 2 L. So you need log base 2 L number of bits to represent L values. For example, let me take a simple example. Let's say you have four values, four distinct values, 0, 1, 2, 3. There are four values. So just tell me how many bits is required to fully represent these values. You will see it requires, actually there are four values, right? So log base 2 4, 2 bits are required, right? And most common representation are, let's say for 0 you are using 0 0, for 1 you are using 0 1, for 2 you are using 1 0, and for 3 you are going to use 1 1. See, you need to have 2 bits for each of these samples. So if there are 4 sample or 4 distinct values, you need to have log base 2 L bits per sample, per sample, or per uh, yeah, per sample. So when I take, let's say, this particular MNTS, which is basically a scalar, can take any value between 1 and 2. What does that mean? It can take infinitely many values, right? Let's say pick any numbers, say like 1.12, 1.312, 1.59, like that. So there are actually infinite number of values possible in this interval 1 and 2. So if I go by this rule to represent MNTS to infinitesimal precision, what I mean by that, if it takes value, let's say 1.95, it takes value 1.95237 or something like that, I need to exactly store it. And for that, basically, if it can take infinitely many values, how many bits I am going to require? If you replace the L here by infinity, what is the result you are getting here? Log of infinity is another is infinite, right? So theoretically, if I plan to store MNTS to infinitesimal precision, that is the exact value, I need infinite bits to represent just one sample. So this is the uh, underlying phenomena that is happening. Two important things: this is a scalar value, this is the value of M sampled at particular this time instant. This time instant can take any value between 1 and 2. So there are infinitely many values, so it can take infinitely many values. And if I plan to store exact that value, I have already seen, if I have L distinct values, I need to have log base 2 L bits to transmit or store that particular sample. So for MNTS, which actually take infinitely many values, I need infinite number of bits to represent that. Remember, imagine just to store one bit accurately. Of course, that is not possible because these zeros and ones are stored in memories, right? And your memories are always finite. You can always store or transmit finite number of bits. So nowhere it's possible to have infinite bits just to represent one sample, right? That is actually where quantization comes. So what is the goal of this sampling here? This sampling I do here that we talked about in the previous session also. These are information bits, right? So the goal of sampling is to obtain the information bits. What does quantization do? Quantization maps the samples to a discrete set of values that can be either used to be store them or that can be used to transmit them. So that is the goal of quantization. You pick any sample and you map them to a only discrete set of values. You cannot map them to actually infinitely many values. That is not possible because we have already seen if I try to do that, I actually need infinite number of bits to store or transmit even one sample. That is not going to happen. So that is where quantization becomes the lifesaver. It comes and it says, okay, I am going to map the sample not to infinitely many values but only to a discrete set of values. So the number of bits per sample that is required is actually finite, and that will allow you to either store them or transmit them in a practical scenario where you have finite resources in terms of transmission or in terms of memory. So how it is done? So I guess the motivation behind quantization is kind of clear here. Now how it is achieved, and of course you can get this intuitive idea that if I am sacrificing, in the sense that for accurate precision I need infinite many values, but I am actually mapping to discrete set of values, so there should be some kind of information loss. So our next goal is to how to minimize that or how that actually works. So let us check this out. Let me introduce a new slide here. So let us go into the maths part of it. So mathematical foundation for quantization, if we call it. So let us denote something like Vk, and Vk we call it kth quantization level. Remember in earlier slide we talked about quantization is all about mapping the sample to a discrete set of values. You can consider values at levels also. So it's about mapping, you are mapping the sample to a discrete set of levels. So among this, Vk is the kth quantization level, and G is actually, let's say, the quantization function you are talking about, and M is the message signal, of course. So this is quantization function here, and here your M is of course a sample. So kth quantization level means the kth discrete value, right? Kth discrete value, and it must lie somewhere, right? So it should lie between, let's say I'm calling it mk and mk plus 1. So what do I mean by that? Whenever the sample here takes value between, let's say, mk and mk plus 1, remember the interval of this kind is always going to have infinite number of values between them. So even if I am talking about, let's say, two numbers 1.92 and 1.95, how many numbers are actually possible inside? There are infinitely many numbers in this interval. So similarly, in this interval also there are infinitely many numbers. So sampling, what we do, we map this entire interval to a discrete value, that is vk. That is what I mean by here. So whenever this m here, that is your sample, is going to take value in this particular interval, I am just mapping it to vk. So what kind of mapping is that? So this is an interval, and in this interval there are infinitely many values, and this is a scalar, right? So you can clearly say it is a many to one mapping. It's a many to one mapping. So you are basically mapping the entire interval, whichever infinite number of values, no matter what value in this interval the message takes, you are going to map it to vk only. That is fixed, that is a scalar number. So that is actually what you are doing in quantization. So let us move to our next question. So this here talk about the quantizer. Quantizer are the your way which enforces or which performs the quantization, and there are different quantizers. So here they are talking about uniform quantizer with an even number of quantization level is known as which of the follows: mid-rate quantizer, the delta quantizer, mid-rise quantizer, or DPCM quantizer. So there are key important terms here. First one you see here, see quantizer we understand from the previous one. The quantizer is some module which perform the quantization, but here we are explicitly talking about uniform quantizer. So there should be some uniformity in the way they work or something of any sort. Second thing is that uniform quantizer which have a feature, what is that? Which is even number of quantization level. So we are talking about a quantizer which has two features. One of them is its uniform, and second feature is it has even number of quantization levels. So let us see what do we mean by uniform quantizer. So when your quantization levels are uniformly spread, that is what you call uniform quantizer. We'll do a visual experiment about that. So what I mean by that, but you can get the idea, right? I mean, we talk about the quantization levels here. So let's say if your quantization levels are something like this, let's say vk here you have vk plus 1, here you have vk minus 1. So there are a few other numbers. So what I talk about uniform quantizer means this gap and this gap are going to be equal. So that is what we mean here, that your quantization levels are equally spread. and this is what you call as uniform quantizer. Now we talk about the even number of quantization level. So we take a non-trivial example of that. So we assume a uniform quantizer with 4 quantization levels. So we talk about a uniform quantizer with 4 quantization levels. So what do I mean by that? Let us talk about these intervals. So let's assume what the message do. So let's say that samples, by the way, when I say samples, I mean the sample of the message original signal. So samples, let's say, take values in the interval -2 delta to 2 delta. So your sample never takes value out of this interval. That means these are the max and min values of your whatever original analog signal you are sampling from. Those are the maximum or minimum values. So this interval I am breaking into 4 parts: -2 delta to minus delta, minus delta to 0, 0 to delta, and delta to 2 delta. See, I have broken down the entire interval into 4 parts. So these are 4 intervals. And for each of this interval I am giving them one quantization level. Remember what we talked about here, an interval being mapped to a scalar. That's what I am going to do. So I am going to pick 4 quantization levels. For this interval I am picking -3 delta over 2 is the quantization level. For this one I am picking minus delta over 2. For this one I am picking delta over 2, and for this one I am taking 3 delta over 2. So what I mean by that, this entire interval, whenever the sample takes value, any values in this particular interval, it is going to map, like the quantizer is going to map to a single discrete level, that is 3 delta minus 3 delta by 2. Similarly, for this interval I am going to map into minus delta over 2. For this interval I am going to map over delta over 2, and for this interval delta to 2 delta I am going to map it to 3 delta over 2. So there are 4 intervals and there are 4 quantization levels. So we have a uniform quantizer with now 4 quantization levels. You can see that gap between here to here is delta. Same here, same here. So till now we have a uniform quantizer which have these 4 quantization levels and uniform spacing. So uniform quantizer with 4 quantization levels that we have now. Now let us draw its characteristics, or to just visually see how it's going to happen, this quantization process. So let us denote our the intervals here. Let's say this is minus 2 delta, this one here is delta, this one here is, sorry, this one is minus delta, this one here is delta, and this one here is 2 delta. Similarly in y axis also you need to have delta minus delta minus 2 delta 2 delta here. So this is the characteristics of your uniform quantizer. See, this step here is at delta over 2, this is the quantization level. This one here is 3 delta over 2, so this is the quantization level. If you plan to draw like this is the quantization level minus delta over 2, and this is the quantization level minus 3 delta over 2. And we can see here just to give you an example here, when this g we know is a quantization function, gm takes value delta over 2 when your sample takes value between this interval, right? So for this uniform quantizer with even number of quantization level, we are observing one particular kind of behavior. I believe you have also noticed that when it passing through this 0 here, the level 0, this is 0, it has a rising characteristics, right? So let me write it down. Rising characteristics when passing m equal to 0. So this particular quantizer, what is actually saying, let's say in this particular interval 0 to lambda, this quantizer is going to give you a flat value of delta over 2. The moment you cross this interval 0 to delta interval and enter into delta to 2 delta, for this whole entire region the quantizer will produce a flat quantization level of 3 delta over 2. Similarly, in this interval 0 to minus delta, it will give you a flat value of minus delta over 2, while the moment it enters the interval minus delta to minus 2 delta, it will give you a flat quantization level of minus 3 delta over 2. But this uniform quantizer with a even number of quantization level show this particular behavior always, no matter your quantization level become 6 or 8, as long as it's even, you will, whenever you draw the characteristics, you will see that it will have a rising characteristics when it's passing through this m is equal to 0 point. So that is why these are actually called mid-rise quantizer. So a uniform quantizer with even number of quantization level always when passing through 0 has shown this kind of rising behavior. Rising in the sense it is moving from quantization level minus delta over 2 to delta over 2. This rising characteristics we are talking about, which gives the uniform quantizer with even number of quantization level a common name which is a mid-rise quantizer. By the way, one thing I forgot to mention here. So, okay, let me just write it down here. Uniform quantizer with even number of quantization levels is called mid-rise quantizer. And by the way, I guess you have already noticed that whenever this I'm mapping those interval to quantization levels, we have particularly chosen quantization level to be the midpoint of quantization interval. And this is something quite intuitive, and this is just not a coming out of nowhere. It has a reason. We'll look after that in the later part of this session. So we have already talked about quantization. What does quantization actually mean? And we have seen one particular kind of quantizer, which is uniform and with even quantization level. So let us move to our next question, which deal with another uniform quantizer, but now it changes with now the quantization levels are odd. Of course, this also has some different feature than a uniform quantizer with even number of quantization level. Now see, one thing is uniform between them, it's uniform quantizer. One thing is same between them, that is they both are uniform, but the distinction is also important. The earlier one we talked in details, having an even number of quantization level. This one here has a odd number of quantization level. So let us just see what does the distinction brings to the plate. So we are going to discuss uniform quantizer, but before we get into the maths part, we will like to have the visual explanation, because that explains things better. Of course, we can later move into the math part anytime, but if our intuition is kind of okay, then I guess the things becomes kind of easier. So we are going to discuss a uniform quantizer. Sorry about that. Uniform quantizer with 5 quantization levels. So what do you actually do here? Let us pick 5 interval. Similar to with even number quantization level, what we consider here, that samples takes value in this interval, right? Let us consider now the samples take value in the interval minus 5 lambda over 2 to 5 lambda over 2, right? So again, similar to earlier, we are going to break into 5 different quantization levels, 5 different which is given by one is minus 5 lambda over 2 to minus 3 lambda over 2. This is one interval. Another interval is minus 3 lambda over 2 to minus lambda over 2. The third interval is minus delta over 2 minus minus delta over 2 to delta 2 over 2. Our fourth interval is delta over 2 to 3 delta over 2. Our fifth and last interval is 3 delta over 2 and 5 delta over 2. Now what we are going to do here, we are going to map each of these quantization interval, sorry, it should not be levels here, these are intervals, sorry about the mistake. We are going to map into 5 different quantization levels here. Similarly, I am going to pick the midpoint, that is no point for guessing that. This interval we are mapping to minus 2 delta. This one minus delta. This interval we are mapping to 0. This interval we are mapping to their midpoint, which is delta, and this interval we are mapping to 2 delta. So now, unlike the previous example, we have 5 different quantization levels, and let us try to draw the graph for that. How does this actually look like? Now already from previous example we know in y-axis we have those quantization levels, and in x-axis we have quantization intervals. So let us mark our intervals first. We have minus 5 delta over 2, minus 3 delta over 2, minus delta over 2, then comes 0. Here we have delta over 2, 3 delta over 2, and 5 delta over 2. Quantization levels, let us map the quantization levels only, that are we have 0, that is anyway. Then we have delta, let us mark this is delta, this is 2 delta, similarly minus delta, and here minus 2 delta. Now we know that for this interval minus delta over 2 delta over 2, your quantizer is going to map the whole interval to 0, right? So let me just shift the position of this indicator so that the graph becomes smooth. Minus delta over 2, this is delta over 2. Okay, so this entire interval is mapped to 0, so this is basically a flat line. if we see from the quantizer perspective. This entire interval is getting mapped into 0. The moment it goes out of this interval, that is, it moves into another segment, that is this interval here, delta over 2 to 3 delta over 2, we know that the whole interval is mapped to a value of single delta. So it's like this, there is abrupt rise here, and this is going to hold for the entire interval duration. The moment it shift the sample value shift from this interval to the interval 3 delta over 2 to 5 delta over 2, the quantizer map it to 2 delta. Similarly here, the moment your sample falls go beyond this interval to minus delta over 2 minus 3 delta over 2, it become quantized to minus delta, and when it moves to minus 3 delta over 2 minus 5 delta over 2, is quantized to minus 2 delta. So this is what a uniform quantizer with the odd number of quantization level, this is going to be its characteristics. Now what is the important distinction with the uniform quantizer with the even number of quantization level and the uniform quantizer with the odd number of quantization level? You can see here, when we talk about even number of quantization level, when it passing through that m is equal to 0, you see the quantizer behavior has a rising characteristics, right? When passing through 0, that's important. You just compare with this scenario here, there is no rising characteristics here, it's flat when it passing through 0, and that behavior is going to remain same no matter whether you use 3 quantization level or 5 quantization level or 7, as long as it's odd. This part, when it's passing through 0, it is going to remain flat. So let us write that. So your quantizer characteristics, it flat at m0, and this gives it name. For even number of quantization level, it was mid-rise quantizer. For odd number of levels, since the characteristics is flat at m is equal to 0, it's called mid-trade quantizer. So this is the distinction between the uniform quantizer with the even number of quantization level and odd number of quantization level. Now it's a good point to discuss about why we actually going to pick the middle point of any interval as the quantization level corresponding to that particular interval. What is the reason behind that? So let us pick this interval from this uniform quantizer with the odd number of quantization interval. We have already mapped this interval here, minus delta over 2 to delta over 2. This interval is mapped to 0. So of course it means that no matter the sample takes value in this interval, what value interval, as long as it's inside this interval, it is going to map to 0. So earlier we talked about that there is going to be a trade-off, because in quantization you are actually discretizing things. That means we, in the earlier motivation we talked about, we actually need infinite number of bits to represent particular samples ideally, if you want to have infinite precision, but that is not possible in practice. You have finite number of memory, and you can only transmit finite number of things. So that is why you go to quantization. Basically you don't have this, you don't try to store the each and every value of this interval. You are going to map the whole interval to a discrete value, and then you are going to store it, but that comes with a price, and the price is something called quantization error. So what does this quantization error means? Consider three cases. Let's talk about the sample taking the value 0 actually. So 0 falls in this interval, right? So if the sample itself takes value 0 and you map it to 0, you can say okay, there is no error, my sample value is 0, my quantizer is mapping it to 0, no issue. What is the problem? The problem comes when the message signal is not uh, like the message sample is not 0 but some non-zero value in this interval. For scenario, for one extreme, let's say the message sample takes value minus delta over 2. So your original sample value is minus delta over 2, your quantizer is going to map it to 0, right? So there is going to be some quantization error. And what is the quantization error amount? It's minus delta over 2. If you take absolute value, it's actually delta over 2, but let's keep it this way. So when your message signal is minus delta over 2 and you map it to 0, you actually have a quantization error of minus delta over 2. Similarly, go to another extreme. When the message signal take value delta over 2, you are again going to map it to 0. So in that case, the quantization error is again delta over 2. So you can see that quantization error comes with a price, and we quantify this price as the quantization error. And that is also the reason we are going to pick the midpoint here, because if we don't pick the midpoint, let's say I pick this instead of 0 I pick delta over 4, what will happen? Now for when m takes value delta over 2, your quantization error will become less, like delta over 4 here, because delta over 2 minus delta over 4 will become delta over 4. You can say find my quantization error is less. But imagine the scenario when actual message value is minus delta over 2. In that case, it will actually going to add up, and your quantization error absolute value is going to be 3 delta over 4, which is greater than delta over 2. So actually when you choose the midpoint, you limit the absolute value of quantization error to its minimum. Any more you deviate on both direction, be it from the towards the left or right, your quantization error corresponds to other extreme increases. That is the reason you go for the midpoint. So let us see that how you are going to kind of have the uh, statistics of the error, like what is the strength, how often they should appear, because these are instantaneous values, right? I mean that there are going to be like millions of samples in practice, and each interval getting mapped into one of these random values. Quantization error appear random, so you cannot track each and every quantization error. You need a kind of second order statistics or the behavior, like let's say on high level you can say on average what is the amount of quantization error we are going to encounter. These are the things we are interested in, because you cannot analyze the quantization error, like you can, because that comes with a lot of overhead. So it's always we try to analyze the the statistics of that error. That is what we are interested in. So let us see how we can compute that. So this delta here, I am calling it as a step size. That name is kind of trivial only, because you can see that this interval is mapping itself to the value delta, and the next interval is mapped to 2 delta. So this step size is what I am calling this thing as a step size. So you can see that step size can be low or high based on your choice. That is pretty much your uh, quantizer choice, how much step size you are going to keep. So this is what we call quantization interval length. So let's say the message signal I sampled takes value between minus m to m. That means the samples I am obtaining from it is going to take any value between in this interval. That makes the dynamic range as 2m, right? Because uh, you can say that dynamic range is basically the length of this interval. So if it can vary from minus m to m, the dynamic range is 2m. And if you are already fixed the step size here and your range is this, so how many levels you are going to have is this number of quantization levels is 2m over delta, and this is we call L. Now you can see clearly the the relation. For example, you can see that quantization error is directly proportional to your step size. So if you actually choose to have a small step size, that is going to directly reduce your quantization error. But what does it mean by having a small step size? Your denominator here becomes small, and if your range is fixed, that means your number of quantization level is going to increase. Basically you would need more quantization level, and you can actually correlate with this idea that more the quantization level your quantizer have, it's more expensive, be it computationally or in terms of the hardware implementation to implement it. The simplest kind of quantizer is the which have a minimum number of quantization level, maybe like one step quantizer, which is like either output 0 or 1. That is the easiest one to implementation, inexpensive, everything. And the moment your number of quantization level increases, your quantizer become expensive in terms of implementation, also in terms of computational complexity also. So you can see here also you have a kind of trade-off. If you reduce the step size, yes, your quantization error is going to be less, your quantization quality will be better, but you have to have a costly quantizer, expensive quantizer. On the other hand, if you have a simple quantizer which is inexpensive, which is pretty much have less complexity, but in that case you have to tolerate a high quantization error. So it's always going to be a trade-off between them. You have to find a suitable point. So few minutes before I was talking about the statistics of quantization error. What I mean by that, so to of course have the statistics of the error, I need to have the probability distribution function also, right? So probability distribution function of quantization error. So you can actually see that quantization error is uniformly distributed. So what do I exactly mean by that? So if I plan to draw the PDF of quantization error, I am going to have something like this. Let's say your quantization error takes value between minus delta over 2 to delta over 2. Then your PDF is like that. Of course, this amplitude is going to be inverse of his base, because the area under your PDF should always be equal to 1. So if the base is delta, the amplitude here is going to be 1 over delta. So your quantization error is uniformly distributed. Then I plan to compute the expected value of the squared value of the error. So what do I need to do here? Basically I need to integrate this product of the PDF with square, and my integration limits are this minus delta over 2 to delta over 2. So this is the maximum and minimum value the quantization error takes. So what we have here, let us take 1 over delta outside. We have a square dE being integrated over this limit. That means 1 over 3 comes outside, and I have E cube here as delta over 2 to delta over 2. 1 over 3 delta over 2 whole cube minus of minus of delta over 2 whole cube. 1 over 3 delta here, we have delta cube over 8 minus of delta cube over 8. So we have 1 over 3 delta into delta cube over 4, that means delta square over 12. So this is the statistics of the squared value of error. Remember we talk about number of quantization levels being L. In the beginning question, in the first question we discussed today's session, we talked about if we have L discrete values, we need log base 2 L number of bits to represent each of them. You can just put that idea here. So if your quantization level, if your quantizer has L number of quantization levels, you actually need log base 2 L number of bits to represent each of them. Let me write it down. This is also called quantizer resolution. And we have seen that more number of levels is directly proportional to low error, but it incurs more complexity. Let us move to our next question. So this is about delta modulation. Delta modulation is kind of a quite interesting modulation, so we'll talk about that. So the question asks, in delta modulation, the distortion that is going to occur when the signal rise or fall slowly in comparison to the reconstructed signal, what do you term that particular distortion as? Is it granular noise, or it's modulation of offset distortion? Sorry, modulation offset distortion, slope overload distortion, or salt or pepper distortion. So let us talk about how it's related to quantization, the delta modulation, and what it mean by the reconstructed signal. So we already talked about this is your original continuous signal, and of course when you quantize you cannot represent each value to infinitesimal precision, right? So you have a kind of staircase approximation of the original signal. This looks like this, and this comes because of this inherent property of the quantization that you have the discrete number of levels, not infinitely many levels. So accurate representation of original signal to infinite accuracy is not possible, but we have some approximated version based on the discrete levels, and this we call as staircase approximation of original signal. Now where does the delta modulation comes into picture? Let us talk about the motivation first for the delta modulation. So imagine you have a signal which takes value in this interval, let's say minus 1000 to 1000. Okay, it takes value in this interval, and you want very low quantization error. So how to ensure that? You need to have the step size in your quantizer very small. So let's say in this case I consider the step size delta, let's say 1. So my message can take value between minus 1000 to 1000, and its step size is 1 because I want to keep the quantization error, because when your step size is 1 you will have actually quantization error delta over 2, right? 0.5. So when I say I want to limit my quantization error, the parameter I need to change or have is the step size. So these are the two things I have. So what is the dynamic, like how many quantization level will represent here, like how many quantization level we need here? We have already talked about it's a 2m over L, where the 2m is the dynamic range. So the dynamic range here is minus 1000 to 2000, minus 1000 to 1000, so that is 2000, and you have the L is the dynamic range divided by the step size. Step size is 1. So there are, you need 2000 level in your quantizer. So whenever you have 2000 level in quantizer, what kind of resolution you need at your quantizer, or to be more specific, how many bits you require for each level? So number of bits per level we have already talked about, it's log base to L bits, right? And you of course need to round it off to the highest integer here, which is around 11 bits. 11 bits per level. So you have a very good quantizer which is going to keep your quantization error really in check. But since your message have such a big dynamic range, it is going to cost you like a resolution of 11 bits per level. So that is a huge complexity, and this kind of quantizer is really expensive to implement. So that is where your delta modulation comes into picture. So what delta modulation is saying? Delta modulation says that I am not going to quantize each sample. So delta modulation say that don't quantize raw sample values. Rather, quantize the difference between successive samples. So the signals, okay, so here it says that you are supposed to quantize the difference between successive samples. Now successive samples, if your quantization if your sampling frequency is quite high, that is the values in practice, your signal doesn't change really abruptly, right? It's changed small. So the successive samples are of this kind of text values. Let's say it's 990, 992, 994, 997, stuff like that. I'm just picking a one particular interval in the whole message. So if you don't go for the delta modulation and go for the regular quantizer, where you actually quantize each of the sample, you actually need 11 bits to represent each of them. Now what do you do? The delta modulation saying that don't quantize the raw samples like 990, 992, 994, 997. You are supposed to quantize the difference between them. That means if you consider the 990 as a reference, what is the difference with 990 and 990? It's 0, right? It's kind of trivial. What is the difference next? It's your 990 is your reference point and the sample is 992, that is 2, right? Third one is 994, so that is your reference is, now it becomes 4. Now it's 997, so it's basically 7. So stuff like that. So you can see now, if you don't go for quantizing the raw samples and rather you quantize the difference, now you can see the values comes down significantly that you're supposed to quantize. So you can see in this let's say in this particular interval, if my step size remains same, what does that mean? Because I am still willing to keep my quantization error in check, that is lower than 0.5, that is half of the step size. I have my step size below this, but how many levels I am going to have here? The dynamic range changes kind of drastically here, right? Let's say for maximum I'm taking 8. It's 0, 2, 4, 7. Let's take up to 8. Maximum is 8. So now my step size remains same, but the dynamic range of the difference between successive samples is orders of magnitude lower than the actual values. So you did not touch the step size, that means your quantization error still remains same, but you change or you manipulate the dynamic range here. So now you need to have only 8 levels, and so if your quantizer has 8 quantization levels, how many bits you are going to require now? It's only log base 2 8, that is 3 bits. So see, for the same quantization error, earlier you were paying 11 bits per quantization level. That is expensive to implement, and also from a memory point of view, it's difficult to store, difficult problematic to transmit because efficiency is low. Now you just need only 3 bits, so your quantizer only need 8 levels. That's significant improvement, and that is the key feature of the delta modulation. It uses this principle here, that dynamic range of the difference of successive samples are orders of magnitude lower than their raw sample value counterpart. So since you have able to reduce the dynamic range, you can have still low quantization error but with finer resolution, because you now have less number of bits. So it's a heaven from implementation perspective. So let me write that down. Number of bits to represent the quantization level significantly reduced in delta modulation. Therefore, delta modulation drastically reduces the quantizer resolution. Remember what quantizer resolution is? It's the number of bits you require to represent each and every level. And practically it happens, we can actually have a single bit quantizer. So delta modulation enables use of single bit quantizer. That means it's either 0 or 1 kind of decision. So let us just see how it performs that. Let's say at at nth time instant, your true sample value is mn. Mn is true sample, and your mqn minus 1 is the approximation to mn at nth time instant. So the error, this is your true sample value and this is your approximation. So your error is going to be mn minus mqn minus 1. This we call as en. And what is the, by the way, this is the error only, not quantization error. Now the what is the quantized error? Quantized error, this is since we are talking about single bit quantizer, this is a sine function. which takes value delta or minus delta. It's similar to 0 and 1 kind of scene. And by the way, here your sine function, in case you are not familiar with this, it takes value 1 for x non-negative and it takes value 1 for x non-positive. So this is your quantized error for single bit quantizer. Basically it takes the error, quantize it, and this we denote as EQN. So what is the reconstructed prediction? Reconstructed prediction, which we call MQN, is going to be MQN minus 1, your prediction from previous time instant plus the quantized error here. The thing actually becomes clear if we see the plot, what is actually happening. So let us draw that. So of course you would see this is your original signal and this is your staircase approximation. So what is happening here is this value here, by the way let us spot the time instants. So this is nth time instant and this is n minus 1th time instant. So this value is your approximation to mn here, that is this one here. Sorry, so this value is for this mqn minus 1. This is the approximation of mn to nth time instant. So this is your approximation at nth time instant. What is happening, this value, this here is the original mn, which is a ground truth sample, right? You see this one is above your approximation, so that signals you need to move upwards, right? So this is your, you move that, and this value here is what your reconstructed mqn is. So you can see how it's happening. This particular part here, this increase here, what you are seeing, this is your error, right? Sorry, this is not your error exactly. So this blue line is the message signal, and so what I am pointing out is this part here. This is your approximation mqn minus 1, this we talked about, and your original value is this. So the difference between this mn and mqn minus 1 is this part, right? This part I am noting in black, this part. So this is what your error is, that is E of n. And what the value does it take? Your, since your ground truth signal mn is clearly greater than your approximation, en is 0, sorry, n is greater than 0, it's a positive value. So what does eqn is going to be according to this here quantized error, if you are using a single bit quantizer? So eqn is going to be sine function of some non-negative number, positive number. It's going to be delta here. So that signals your reconstructed prediction, which is the mqn, is going to be your previous approximation, that is approximation to mn at nth time instant, which is you have approximated based on your previous value plus this quantized error. So this increment. So this way you can form similar argument when the message signal is falling. You can see from here to here your approximation is higher than your ground truth value. In that case your error is going to be negative. So in that case your quantized error is going to be minus delta. So what that is going to signal, that your reconstructed prediction mqn is going to be mqn minus 1 minus of delta. That means it would be lower than your previous approximation. So when it's rising, the quantized error is positive, when it's falling the quantized error is negative. That's how you kind of track this original signal, and this is what we call about staircase approximation in the reconstruction of the original signal. So delta modulation is actually allowing you to use a single bit quantizer, because the successive differences are quite less. So you can actually have a increment or decrement of size, step size delta, and approximate the signal. But there are certain limitations which is the context of our question and which we will talk next. But let us see what the question is. So it talks about the distortion which occurs when the signal rises or falls slowly compared to the reconstructed signal. So let us move to that particular example. So signal rising or falling slowly compared to reconstructed signal. That leads to this particular scenario. Your message signal shows very small variation, let's say like this. So you can see this is showing very small variation, but your reconstructed signal is it's not slow, or it's kind of rapid. It's like this. Let us draw this. Let's draw another version where we have a small variation in the reconstructed signal like this. So this one here, this one corresponds to, you can clearly say where the jumps are quite abrupt compared to your, it's like signal is varying slowly, but your reconstructed one is varying kind of widely. So that means you're using a large step size, or relatively large step size I should say, in delta modulation. So this we have already seen in this example. So this increment that you show is nothing but the quantized error, which takes value delta or minus delta. And when your this step size becomes quite large or quite large compared to your signal variation, then you are going to see this kind of behavior. Your underlying signal is varying slowly, but your reconstructed signal is kind of moving abruptly up and down, up and down. It's kind of unnecessary. You can see that your original signal has a slope which is very small, and what these things is causing, the large step size delta leads to something called granular noise. When signal is relatively flat, so this you can see that sudden increase and sudden decrease are kind of unnecessary. It's not following the signal, it is just creating unnecessary noise, and that happens when you have a relatively large step size compared to your original signal variation. So this large delta leads to large error between original signal and its staircase approximation, and this phenomena is nothing but called granular noise. To answer our question here, this is granular noise. And the question you might have the opposite scenario when the signal actually rise or fall rapidly in comparison to the reconstructed signal. In that scenario, it is not it is just the opposite. It is called slope overload distortion. Maybe we can discuss that if we have time after finishing this. So here we are talking about your time division multiplexing 20 voice signal which is sampled uniformly, and the sampling operation is going to use flat top samples with 2 microsecond duration. The multiplexing operation include provision for synchronization by adding an extra pulse of sufficient amplitude and also 2 microsecond duration. We are given the highest frequency component of each voice signal is 3 kilohertz, and we are assuming that you are sampling those signals at the Nyquist rate. We are supposed to calculate the approximate silence time between successive pulse signals. So there are few things. So let us break down first. We are talking about time division multiplexing. What does it mean? It basically means you are going to multiplex a different signal in time domain. So how does this scenario happen? So let me just show you. So let's see, there is one message signals, one voice signal, let's call it M1T, second is let's say M2T, and like this you go on, and there are n signals, suppose calling it MNT. So all of them you are passing through, let's say, a low pass filter. and what you have here is a kind of multiplexer which combines all of them. By the way, this is not multiplexer, this one here is, this is something called a commutator. This one I am calling it commutator. So the idea is that all of this signal has its own channel, and what does the commutator do? It picks samples from all this M1, M2, MNT at the same time. So here we get a composite signal, right? Composite signal that is being talked about in the question. You are like time division multiplexing 20 voice signal, so you can take here n is equal to 20, so you have connection to each of these and you're commutating. Basically you are taking each samples from all of them at a particular for a given time instant, and what you have a composite signal, and you pass it through the channel and you obtain the output signal. So what we are going to get here, let's say, let us draw here. By the way, remember it's not a practical, it's a practical flat top sample. So this one here corresponds to M1, this one here corresponds to sample from M2, this one here corresponds to sample from Mn. So your each voice signal has a frequency of 3 kilohertz maximum, so their sampling rate, let us consider their sampling rate as fs is 6 kilohertz, right? Because maximum frequency component 3 kilohertz and Nyquist rate is twice of that, 6 kilohertz. So your fundamental period is going to be how much? It's 1 over 6 into 10 to the power 3 second, right? And if you calculate, that would come out to be 166.67 microsecond. So what is happening in a composite signal? What you do, your this entire duration here is this Ts, because when you time division multiplexing them, you need to fit all of them in this 166.67 microsecond like Ts time interval, because when you move to next instant, that is Ts, the moment that Ts time is passed, there is another sample is going to be ready here, right? So within this 166.67 microsecond, you need to accommodate all 20 voice signal plus one extra pulse, So in 166.6 microsecond, we need to accommodate 20 voice sample from each of them, M1, M2 up to M20, plus one synchronization pulse. So total 21 pulses should be there in this particular interval. And by the way, this one, of course there are 21, the gap between one starting for one pulse to starting of next is Ts over n, right? So the time between each pulse, how much is going to be? There are 21 pulses, you need to fit in 166.67, that means 166.67 microsecond divided by 21, that would come out to be 7.936 microsecond. But here is a catch, remember each pulse, it's not a Dirac delta pulse which have no practical duration, it's a practical pulse flat top samples with 2 microsecond duration. So when I say starting from this pulse to this pulse is Ts over n, which has a duration 7.936, you have to subtract this pulse duration, which is 2 microsecond. This is 2 microsecond. So the actual gap between two pulses is this, but Ts over n is not this. Ts over n is the gap between starting from one pulse to another. That is what you get here, 7.936 microsecond. But we have to consider the pulse duration for each of them, that is 2 microsecond. So then the approximate silence time between successive pulse, this approximate silence time they are talking about, this is this part they are talking about, not Ts over n. This is the one they are talking about. And what is this? This is going to be 7.936 minus the pulse duration 2, which makes 5.936 microsecond. This is going to be your approximate silence time. You have to be careful to subtract this pulse duration. I am repeating again, the time between each pulse is 7.936, but that is this time, this point starting from one pulse to this pulse starting of next pulse, that is 7.936, but each pulse is of duration 2 microsecond. The silence period corresponds to actually this gap between two pulses, not Ts over n, time between each pulses. So that's why you need to subtract 2 from 7.936, which comes out to be 5.936. So the third one is our answer. Let us move to the superhead receiver. It's saying it is having a broadcast frequency of 1 kilohertz and intermediate frequency of 500 hertz. What is the corresponding image frequency going to be? So let us draw the structure once for the superhead receiver. So we have our MT here, MT cos 2 pi FCT. FCT is the broadcast frequency, this is here, and here is your local oscillator which generates a frequency of cos of 2 pi f1 plus f2 t, right? And then here you will have a band pass filter, band pass. Okay, by the way, let me just call it f1 here. F1, and band pass is going to pass the frequency f2. Right? So what does it do? Like input signal having a frequency f1t, this local oscillator intentionally generating a frequency component f1 plus f2, so that when you multiply and pass it through a band pass filter, what you are going to receive, let us just check, mt cos 2 pi f1t cos 2 pi f1 plus f2t. You are going to get mt over 2 cos 2 pi f1 plus 2f2 t minus cos 2 pi f2 t. When you pass it through a band pass filter with center frequency f2, you will get mt over 2 cos 2 pi f2 t. When your f2 is the intermediate frequency they are talking about here, is basically lowering down your incoming frequency. Incoming frequency was 1 kilohertz, but here you are getting at the output is 500 hertz. This is the property of super heterodyne receiver, where the image frequency is lower than the broadcast frequency. Sorry, the intermediate frequency is lower than the broadcast frequency, but there is a issue with image frequency. What I mean by that, if instead of the message signal being cos 2 pi f1t, if your message signal becomes m cos 2 pi f1 plus 2 f2t, f1 plus 2 f2t, what do you think it will happen? If you multiply with the local oscillator output, which is the cos 2 pi f1 plus f2t, you can see here you have f1 plus 2 f2t as the input, and here you have m1 f1 plus f2t. If you pass this output through a band pass filter with centered around f2, you will see you will get another, you will get identical output f2t, because you can see here you have f1 plus 2 f2, you subtract it, you subtract f1 plus f2 from this, you will get a f2 component alone. So you can see that this is not only the signal that will go through this band pass filter, but there is another signal which, if they have the frequency f1 plus 2 f2, where f2 is the intermediate frequency and f1 is the broadcast frequency, they will actually go through this band pass filter also. So they are going to create noise or interference. So that is what we call as image frequency, which creates trouble. This is your image frequency. So f1t is not the only one which this, if you have a signal which your desired signal with broadcast frequency f1t, fine, that will pass through. But if you have some other signal which is transmitted at a frequency of f1 plus 2 f2, that is also going to pass through this band pass filter and create interference from your desired signal. So this image frequency creates trouble. And what is the value of this image frequency? It's f1 plus 2 f2, where f1 is your broadcast frequency, that is 1 kilohertz, plus 2 times f2, that is your intermediate frequency, which is 500 hertz, 0.5. So that means 2 kilohertz. So your image frequency is going to be 2 kilohertz, which is going to cause problem for you. Here we are asked for a GSM multi-frame has 26 frame, each frame has 8 time slot, there are this many bits per time slot, and each bit has this many long. What is the approximate duration of multi-frame? Actually this duration is quite straightforward to calculate. You are given everything. So multi-frame contains 26 frame, each frame has 8 time slot, in every time slot you have 195.3 bits, and each bit is 3.7 microsecond long. So this entire, this many number of bits is being transmitted in a multi-frame. And what is the time required to transmit this many number of bits? If you calculate, you will see it's 150.3 millisecond. So second one is the closest answer. Let us move to our next question. It's talking about signal MIT, which is band limited to 4i square kilohertz each, and your time division multiplexing that we discussed in the question, the previous or next to previous one. So after sampling respectively at the Nyquist rate for each signal, the samples are quantized using L1024 levels and binary coded. What is the bit rate of signal? Now there are key information is L is 1024, that means the number of bits you require to represent each sample is log base 2 L, which is log base 2 1024, that is 10 bits you require for each sample. Now how many samples are going to be there? So you can see if it's band limited to 4, your frequency, let's say if uh, I is going to be 4I square, that means your sampling frequency for this particular signal fsi is going to be 8I square, and your time division multiplexing, so basically you need to sum them up. So number of samples in the composite signal, we are supposed to find the bit rate in terms of per second, right? So what we do that we will first calculate the number of samples, and then we just need to multiply the number of samples with the number of bits required to represent each sample. That would give me the bit rate of the resulting information signal. So what is the number of samples? You can see that for ith signal the Nyquist frequency is 8I square, so 8 I can take common outside, sum over I is equal to 1 to 5 I square times 10 to the power 3, because it's kilohertz, so this many samples are going to be there. So 8 times 1 plus 2 times 4, 9, 16, 25 into 10 to the power 3. So the bit rate is going to be this many samples. What does it add up to? It's 41, 50, 55. So 8 times 55 into 10 to the power 3 into 10 bits per sample, remember. So that many bits per second, so it's 10 to the power 4, and 8 times 55 is going to be 4.4 into 10 to the power 2, so that means 4.4 into 10 to the power 6 bits per second, or 4.4 Mbps. So my bit rate is going to be 4.4 Mbps. So this is pretty much all I plan to discuss in this session. If you have any questions, I would be happy to answer. If you don't, we can conclude this session and we will meet again on next Saturday. So any questions based on whatever I discussed today? Thank you for attending the session. Thank you. So if we don't have any question, then I'll conclude it, and we'll meet next Saturday again. Thank you everyone for attending. Bye.